An accurate and reliable means of measuring the outside air temperature is essential for the safe and efficient operation of the aircraft. Flight in icing conditions can be hazardous. Ice can form rapidly on an aircraft, especially in cloud, and ice buildup can result in a loss of lift, increased drag, and an increase in weight. In addition, a buildup of ice can inhibit the free movement of control surfaces, and damage can occur to the airframe as a result of ice being shed from propellers. Ice ingestion into a turbine engine can cause loss of power and even a flameout. And in piston-engined aircraft, carburetor icing can be a major cause of engine failure. Temperature also affects the density of the air, so it will have a direct bearing on aircraft performance, engine power, and the measurement of altitude and speed.
Measuring the outside air temperature, however, is not as straightforward as might at first be thought, because the movement of the aircraft through the air will cause the air temperature to rise in the immediate vicinity of the aircraft, as a result of friction, or kinetic heating, and air compression, or adiabatic heating. These terms are fully explained in the next lesson. This temperature will not be representative of the true outside air temperature.
It is the true outside air temperature that we need to know. So in this lesson we are going to look first at the basic types of air temperature thermometers in use and their principles of operation. Next, we will look at a typical total air temperature probe of the type used on modern high-speed aircraft. And finally in this lesson we will consider the errors which the instruments are subject to. Air temperature thermometers can be divided into two basic types: the direct reading thermometer and the remote reading thermometer. We will consider the direct reading thermometer first. One of the simplest is the bimetallic thermometer, and it works on the principle that two metals with different coefficients of expansion will expand at different rates if subjected to heat. If these two metals are bonded together to form a single bimetallic strip, the metal with the greater rate of expansion will cause the bimetallic strip to bend. How much the strip bends depends on the temperature rise and is therefore a measurement of temperature. The metals bonded together are often invar and brass.
Invar is a specially developed steel with a low coefficient of expansion. Brass, on the other hand, has a higher coefficient of expansion. If the bimetallic strip is now wound into a coil or helix and one end is held fast, then any temperature change will cause the helix to rotate. This rotation can be used to drive a pointer around a dial, which can be calibrated in the form of a temperature scale.
Simple direct reading thermometers are subject to a number of errors which we will look at later in the lesson, but they are adequate for use in relatively low-speed aircraft. It is often desirable to have temperature information in an electrical form, so that it can be fed to other instruments and systems. Remote temperature gauges work on the principle that the electrical resistance of certain materials changes with a change in temperature. Measurement of electrical resistance will therefore be a measurement of temperature. To measure electrical resistance, a resistance circuit is employed, commonly known as a Wheatstone bridge. We can see here a diagrammatic illustration of a Wheatstone bridge circuit. In basic form, the circuit consists of a power source and four resistors, labelled R1, R2, R3 and R4 in our diagram. For a given voltage input, the current flowing through the resistors will depend on the resistances. If the resistances are equal or balanced, the current flow in the circuit will be zero. If one of the resistors is exposed to the outside air as temperature changes, so will the resistance. This will cause an imbalance in the circuit and a current will flow, which will be proportional to the temperature change. The change in resistance is consequently a measurement of temperature change and can be calibrated. This is an accurate system which can detect even small changes in temperature, and as the system works on the principle of balancing resistances, any fluctuation in the circuit voltage will not affect the accuracy of the system. Let us now look at a typical total air temperature probe of the type used on a modern high-speed aircraft. The probe is usually constructed from nickel-plated beryllium copper, which provides good thermal conductivity and strength. This type of probe consists of an air intake mounted at right angles to a small hollow strut or casing. Inside the casing is a pure platinum wire resistance sensor. Platinum is used because it has a very high rate of conductivity and gives a rapid response to temperature change. Platinum also has a linear resistance change to temperature change relationship, which makes it ideal for temperature measurement. The probe is fixed to the fuselage in a location which minimizes any boundary layer effect, usually the front fuselage. Boundary layer effect is discussed in detail within aerodynamic courses on principles of flight. Here we can see a diagrammatic cross-section of a total air temperature probe. Let us look at how it works. It can be seen that some of the air entering the probe is turned at right angles to pass over the sensing element. This is to separate the air to be sensed from any water or solid particles present. Flow separation is achieved because water or solid particles have sufficient kinetic energy to pass directly through the air intake and exit. The bleed holes we can see in the intake casing allow the higher pressure air escaping from within the intake casing to draw off boundary layer air. An integral heating element prevents the formation of ice. The effect of the heating element on the temperature sensed is small and is not significant. It is also necessary to measure air temperature on the ground. A factor affecting takeoff distance and the takeoff power required is temperature. A reduced power takeoff may therefore be possible, and this is a valuable operational consideration. Without forward movement of the aircraft, air within the sensor casing can stagnate. Stagnated air could give a false indication of the outside air temperature. To re-establish an outside air flow within the probe, an air-to-air ejector or aspirator is used. The principle we can see in operation here is that pressurized bleed air is being drawn from a compressor stage of a running engine or auxiliary power unit and is being fed through the aspirator. This creates a negative pressure differential within the sensor casing, which draws fresh outside air past the sensor element.
Finally, in this lesson, we will look at the errors which air temperature gauges are subject to.
The first is instrument error. This occurs in the manufacturing process, and unfortunately, manufacturing imperfections are difficult to avoid. The second error is
environmental error. This error can occur as a result of solar heating of the temperature sensor. Direct reading thermometers in particular can be vulnerable to this type of error. Solar heating can be reduced by shading, which happens in a remote detector. Icing is also an environmental error.
And thirdly, we have heating error. We will recall from earlier in the lesson that the movement of the aircraft through the air will cause the air temperature to rise in the immediate vicinity of the aircraft. The rise in temperature is caused by friction or air compression as the aircraft moves through the air, and it accounts for by far the greatest error in high-speed aircraft. Low-speed aircraft are less affected by friction or air compression and are therefore less vulnerable to this type of error. In this lesson, we have considered why accurate air temperature measurement is necessary and the problems associated with air temperature measurement. We should also now be familiar with the principles of operation involved in a direct reading thermometer, a remote reading thermometer, a total air temperature probe, and an aspirated total air temperature probe. This ends our consideration of air temperature sensors. Part 2 of air temperature measurement will take us through the relationship between temperature and speed and define static air temperature, total air temperature, and RAM air temperature. It will also look at methods of air temperature correction. A summary of the main points of the lesson follows. Temperature affects aircraft performance. Ice can build up quickly, especially in cloud. Ice build-up can cause loss of lift and an increase in drag and weight. Temperature affects air density, which affects engine power and the measurement of altitude and speed. Kinetic and adiabatic heating will give a false indication of the true outside air temperature. The two basic types of air temperature thermometers are the direct reading and the remote reading thermometer. The bimetallic thermometer works on the principle of two metals bonded together with different coefficients of expansion will expand at different rates. The two metals often used in the bimetallic thermometer are Invar and brass. The remote reading thermometer works on a Wheatstone bridge principle. The total air temperature probe is usually constructed from nickel-plated beryllium copper. In the total air temperature probe, the sensing element is usually made of pure platinum. The total air temperature probe is fixed to the aircraft in a location which minimizes the boundary layer effect. In the total air temperature probe, an integral heating element prevents the formation of ice. An aspirated total air temperature probe uses